So when we have a solid non-conducting cylinder, we can also say it's a wire. The charge is not distributed on the surface like a conducting cylinder or a hollow cylinder. The charge is actually distributed in the entire volume, and the charge density is nothing but charge by volume. So in the last class we saw that we talked about the surface charge density. Here we're going to talk about the volume charge density. Okay, so here also we can actually draw a cylinder here. It can be a wire, okay, or it can be a cylinder. Let me just draw a cylinder. And as I said, if we're talking about something as an infinite length, that means the distance is small compared to the length, so that's important. Okay, so this is my cylinder, which is non-conducting, at the same time it is solid. Okay, so we have got the material even inside. Okay, so such cylinders will actually have a charge distribution which will be distributed throughout the cylinder, so we don't have it on the surface. So that is the basic difference, and that's why even for solving it the approach is different. Okay, so we can have different regions for this. Okay, we can have different regions for this. So what I will do is I will find out the electric field. One will be inside and the other will be outside. So for inside, let's say I'm taking it here at a distance this. Okay, this is at a distance r, and for this again I have to draw a cylinder which may be imaginary. So we will draw an imaginary cylinder symmetric about the axis. Okay, on this side it's R, that means on the other side also it's R. So this is my cylinder which is inside. Now in the last class we saw that when we are talking about inside, the charges are on the surface. That means any cylinder drawn inside does not enclose any charge. But as per Gauss's law, if you want to find out the electric field, it should enclose any a charge, otherwise the field is zero. So this one is actually enclosing a charge. Okay, so let's say that the radius of this is capital R. Okay, and now we can talk about the two cases. So the first case is inside, and by inside we mean that this small r is less than capital R. Okay, the approach will more or less remain the same, and just like yesterday we said that the flux will be actually part of three: phi 1, phi 2, phi 3. Same logic here. Phi 1 and phi 2, let's say this surface and this surface, the surface vector area vector is perpendicular to the electric field, so that vanishes. I'm only having phi 3. Okay, so phi 3 means you have to find out what is the flux coming out of this Gaussian surface. So that means you have to take the E dot area, and the total area for this is nothing but, it's a cylinder, so 2 pi r is this, and let's say the length of this cylinder is f. Length of this cylinder is f. Okay, so this is we have to take. So now we can use our Gauss's law. We can simply say that E into 2 pi r l is equal to the charge inside divided by epsilon naught, right? But if we are talking about this concept, the charge is equal to nothing but rho into the volume. Okay, now this is basically a cylinder. Now we are talking about the charge density which is there in the actual cylinder, not in the Gaussian surface. Okay, so we have to consider that uh, charge distribution when we are considering it outside, but when we are considering inside, there is no point of taking the charge distribution of the entire cylinder. We have to consider what is the charge enclosed by this cylinder. So for that, what we can do is we have to know what is the charge enclosed by this particular cylinder. So for that, what we do is we find out what is the volume of this cylinder, because this cylinder is also enclosing the charge, because the charge is distributed in the cylinder. So let's find out how much is the charge. So we have to find out the volume. This was the formula for area. Volume, it's nothing but uh, meter cube. So for a cylinder, it is pi r square m, right? So that means here what we can do is charge is nothing but rho into pi r square l divided by epsilon naught. Okay, can do our cancellations. This and this, pi and L, and this R also goes. The square is not there. So if we take it, E is equal to, on the numerator we have got rho into R divided by, we have got 2 times epsilon naught. Okay, 2 times epsilon naught. So this is important. Again, you have to kind of remember this if you want to do numericals on this, but if you do some mental maths, it's not very difficult to remember. Okay, but here we do observe that this E, or the electric field, is proportional to R. So if it's inside, the electric field is proportional to R. A very important point that you should know. Okay, because if you look into the previous case, electric field does not exist, so there is no proportionality here, but here inside it is proportional to R. So that was the first case. Let's find out what happens outside. Okay, so the second case is outside. So I don't think we need to draw the diagram again. I hope it's quite clear. R will be greater than capital R. Okay, so if we take that R is greater than capital R, that means we are basically considering a point outside the cylinder. So maybe we can take the help from the previous diagram, and we can think about this as his diagram, and we can think about okay, again we can actually draw it, right? let's draw this let's draw this symmetrical cylinder of length L. Okay, this length might not match with the inner cylinder, not necessary, we are just saying it's of length L. Okay, so now if we again do this, what we can do is simple, the same thing. Now this E into 2 pi RL is equal to Q inside divided by epsilon naught. Now the main logic comes in. The logic is, previously this small radius r enclosed the charge that was actually in the Gaussian surface, but now we have got this small r which is outside, or greater than capital R. It cannot have a charge which is more than whatever is enclosed by the inside cylinder, because this is an imaginary surface, this does not have any charge. Okay, so this will enclose this entire charge. So this time you don't have to take small r, you have to consider capital R when you take the volume. Okay, this is the main logic, or very main important part here. So here what we can do is, this would be nothing but volume charge density into volume by capital R square L divided by epsilon naught. Okay, so we can again do our thing. Let's cancel this is R, this is pi, this is L. We can actually cancel this out. Okay, so that means this time the formula is slightly different. E is equal to rho capital R square divided by 2 times epsilon naught R. Right, this is our formula. This time this is our formula. So these things are important. Any kind of tricky questions for your exam might be from this. If you know the formula, if you understand the logic, you'll be comfortable with this. But here what we see, that the electric field that we have is proportional to 1 by R. See, this is interesting. When inside it was proportional to R, when outside it is proportional to 1 by R. That means again we can actually draw a graph, right? So let's try to draw a graph here. Okay, so we do have the cylinder. Okay, or maybe I'll draw a broader cylinder. Like broader one. So till this point it's inside, and then it is outside. Okay, so we can see that for inside, okay, E is proportional to R, and for outside E is proportional to 1 by R. Okay, this is my inside, this is my outside. Okay, if you look into the border, this R square and this will become equal. Okay, that will be the maximum potential, oh sorry, the maximum field that we know. So let's just do the bordering here and draw the graph. Okay, so inside E is proportional to R, that means it is directly proportional. This side we have got E and this side we have got R. Inside it is directly proportional, that means it will be like this, right? As R increases, electric field will increase, but outside as R increases, the electric field will reduce. It is 1 by R, so it will be something like this. So here E is proportional to 1 by R, and here E is proportional to R. Okay, so that's the idea behind a hollow and a solid cylinder. If you take a solid conducting cylinder, the charge will always reside on the surface. But if you take a non-conducting cylinder, the charge gets distributed within the cylinder or sphere, okay, and so on. So if you want to find out what is the electric field because of a sphere, what you can do is you can just change the formula. That's it. Okay, you have to just take the volume separately. That's it. Okay, so if you take a sphere, if you want to find out the volume 4 by 3 pi r cubed, okay, the formula will change there. It's not a cylinder anymore. Okay, the surface area will change. Okay, 4 pi r square, so that's there. Here we have taken 2 pi r n, so that's the surface area. So the formula, that changes the volume and surface area, but apart from that, more or less everything remains the same. Okay, so here also, if you just want to consider it for, let's say, a sphere. Okay, this is something which you can take it as a homework and practice and see what's the answer. Check out and keep the final answer with you. Okay, so you can have a solid conducting sphere. Okay, and a hollow conducting or non-conducting sphere. Okay, this would be our case one, where we can say that the charges are distributed on the surface, and we can use formula like the volume is equal to 4 by 3 pi r cubed. Capital R, small r, depends on which case you are considering, inside or outside. Okay, inside, if you take it outside, they will get some, and inside it will be again 0. So for inside, electric field is going to be 0 for inside. The logic will remain the same. For outside, you do the calculation, take it as a homework. And if you want to find out the area for a sphere, 4 pi r square. Okay, so these things will be handy. And the second one would be solid non-conducting sphere. Okay, so here obviously you'll use volume. Here volume is not required. You'll see mostly you need area. Here you need the formula for volume. So that's for conducting and sphere. That's important. So this was talking about volume many a times. Now we are going to talk about a plain sheet of charge. Okay, so that's there. Let's talk about a plain sheet of charge. Again, we can say, depending on the distance, it might be an infinite plane sheet of charge. Okay, but it simply says that we are talking about a two-dimensional picture here. So when we're saying it's a plane sheet of charge, we can just take up a sheet. Okay, and let's say this is your plane sheet, and let's say the charge is distributed. Okay, it's not mandatory that it should be a positive charge every time. Okay, it can be a negative charge as well, but we can consider it having only positive charges. That means the electric field will be away. If it is negative, only the direction of the electric field will change. Apart from that, the approach will more or less remain the same. Okay, and the question says that you basically have to find out the electric field at, let's say, a point P, which is at a distance x from this plane sheet of charge. Okay? And this distance is not very large. Okay, so we can say that this is at a distance x from this plane sheet of charge. Now here also we actually have to construct a Gaussian surface around this plane sheet of charge, which is more or less symmetrical in nature. And if you see the logic here, you can do different kinds of structure. You can actually draw a big cube, but a more convenient would be to actually draw a cylinder. So let's draw a cylinder around this plate sheet of charge. So imagine this is a diagram, two-dimensional diagram, and I'm drawing a cylinder, a three-dimensional cylinder across it. Okay, so this is my plate sheet of charge. So if you look into the area that is being covered here, it should be this. This is the area being covered. So I have drawn this Gaussian surface. So whenever I want to use the Gauss's law, I have got three things to do. The first thing, draw the main image, see at what point you are finding out the electric field, and then imagine the surface which will be symmetric and draw that surface. Okay, so we have drawn a cylinder here. Now here also we have got three surfaces. Let's say this is our first surface, this is our second surface, and obviously this is our third surface, the curved one. Now if you look here, you know, the charge is distributed here, that means the electric field is in this direction. The area is also in this direction, perpendicular to the surface, as we know. That means theta is equal to 0 degree. Here also it's the same thing, it will always go away. So E dA, so theta is equal to 0 degree. But in this case, the area is in this direction, sorry, but E is in 90 degrees. So that means theta for this surface is 90 degree. Now we can use the same logic and try to use it. Okay, so we have to find out the electric field at a distance x. Okay, so E at distance x from plate. Okay, we have to find it out. So this time it's area, so we're going to take the formula for area density. So that is charge by area, charge by area. So that's why, this charge distribution is very important. And the Gaussian surface is a cylinder. Okay, so if you want to find out what is the flux phi total, okay, that will be because of three surfaces, phi 1 plus phi 2 plus phi 3. But phi 3 is this, theta is 90 degree, so obviously phi 3 will become 0. So this is the thing, don't get confused. Phi 1 and phi 2 will be here. In the other cases we have seen phi 3 exists, phi 1 and phi 2 vanishes, but that was a cylinder which was in this direction, right? It was vertical, but it is horizontal cylinder, and that's why the region changes here, right? So here area, so let's not complicate things here. Let's say the area is A. Okay, this area is A. So if I want to find out this, I can simply write it down as E dot dA cos 0. So I'll take it as this. This is also E dot dA. Cos 0 is 1, so I will just keep it like this. The 2 times electric field can be taken out. Integration of dA. Let's say the area is A, so I'll write it down as 2E8. Okay, so that's my total flux. And now we can use the Gauss's law. Sigma is equal to charge by area, so it is Q divided by A. So that means my charge is equal to sigma into A. Let's do this and put the Gauss's law. So Gauss's law says that this flux that we have is equal to nothing but the charge enclosed by the surface divided by epsilon naught. But the charge, we know it is nothing but sigma into A divided by epsilon naught. This A and this A will get cancelled. So that means the electric field is equal to sigma by 2 epsilon naught. This is a very important formula. You have to remember this. Don't mix up 2 epsilon naught. It is 2 epsilon naught. Okay, don't write it epsilon naught because we are considering a plane sheet of charge. Okay, that's very important. Okay, so this formula is valid, or you can say in a way, mostly the formulas that we have written are valid. Only in this case, okay, that x that we are considering, this x, okay, is actually small. Okay, if I put on this board a very small ant for him or her, uh, look in all direction, it will see that it's just a board. So for that object, the board is infinite. Okay, so in a way we can say this x is small compared to dimension of sheet. Dimension of sheet. If this is the case, then only this formula is valid. Otherwise, it will be complicated. Okay. But we can see one more interesting thing here. This electric field that we're saying is independent of x here. For a sheet, it is independent of x. Independent of x. What does it mean? It means that whether you consider it at this point or this point or this point or this point, at any point, the electric field will more or less remain the same. It does not depend on what is the value of x. Okay, so I will just give you one problem to solve, and it's not, you have to use a bit of logic here. We have got two sheets now. We have seen it's one sheet, we can say it's a two sheet. So it's a kind of a capacitor kind of problem. Let me take, there are two sheets here. This is one, and this is the second sheet, and both of them will obviously have the charge distribution, right? And you can find out the electric field because of these two sheets at different points. So I'm giving you 3 points to check the electric field. This is my first point. Let's say A. You have to find out what is the electric field at this particular point. Let's say we have to find out what is the electric field at this particular. And thirdly, find out what is the electric field at these points. So you have to find out what is the electric field at these 3 points. Okay. So if I want to replicate a capacitor, what I can do is, let me make this uh, change this problem a bit for you. We are replicating a capacitor. We know a capacitor will have a parallel plates. One will be positive, one will be negative. So let me put negative here. Okay, I've already told you, if it's positive, the electric field will be in this direction. If it's negative, the electric field will be in this direction. Okay, in the opposite direction. So that's important. Okay, so using this logic, you have to find out what is the electric field at point A, at point B, and at point C. And for this, we can use the fact that the electric field due to a plane sheet of charge at any point is sigma by 2 epsilon naught. We don't have to derive this for this particular problem. It's already, we have the information. Sigma is equal to, sorry, not sigma, electric field is equal to sigma by 2 epsilon. So using these three facts, you can find out the answer to this.